All right, let's take a look at these questions that we had during breakout groups in class today. We're really going to focus on this one. We'll come back to this when we talk about Lagrangian optimization. Also, just a quick note before I forget, your quizzes, not your final exam quizzes, which we'll talk about, but your quizzes, these are low stakes, so feel free to resubmit to improve your grade. And then also those course evaluations, check your email inbox to see details there about getting a little bit of extra credit as long as enough people fill out those evaluations. So we've got this equation. Now, I took a swing at it and something messed up. So let me take another swing at it. I'm going to start from here. And let me also just copy out some details. So z is equal to 3x cubed minus plus 1.5 y squared minus 18xy plus 17. So I took a swing at it and I did what came instinctively and it just didn't work out. And you know what? Sometimes that happens. So when that happens, the best thing to do is usually just to start from scratch. So in this case, just to minimize the chance that you're watching me fumble over a bunch of nonsense getting nowhere, I'm going to start the way the textbook does this, which is clever. Right? Now, in general, when we're trying to solve these problems, there are formulas we can follow, there are procedures we can write out, like we did here about the general idea of how to optimize a three-dimensional function. But really what this boils down to is we can put these together any number of ways and solve, and who knows what we get. We should get the right answer, but there's no one correct way to get to the right answer. Sometimes one way will turn out to be quicker and more convenient than another way. And honestly, my advice for how to figure that out is if you start doing something and it becomes a mess, maybe take a step back and try an alternate approach, and maybe that alternate approach gets you there a little bit faster. So let's see what we've got here. Maybe flatten this out a little bit. So starting with zx. Now let me also take a step back and lay out some of this logic, why we're doing this. So we're taking this first partial derivative with respect to x. And what that's doing is that's telling us in our underlying function, when we consider it in the x dimension, right? So let's say moving left and right. In that x dimension, how do we see z change? Is it going up like this? Is it going down as we increase x? That's the question we're asking there. And we're looking for where is it flattening out, right? And we're going to be doing the same thing with y. We're asking, how does the slope, what is the slope with respect to y in that y direction, treating x as a constant? So at different values of x, we're going to have different results, right? In this case, we actually have a nice, relatively easy function here to understand. So let's just say that here is 0, 0. So here's our y-axis along the spine. Here's our x-axis here. And here is the origin. What's going on at the origin? What's the slope with respect to y? Well, if y is 0 and 18 is 0, or sorry, x is 0, then, hey, the slope is 0 at 0. Well, that's convenient. Cool. So at 0, at y equals 0, we have this flat slope in the y direction. What happens as we change x, right? So let's increase x. Well, now our slope is going to be still 3 times 0, but now we are making it smaller. We're making it negative. Let's see, negative in the y direction. So here we're y. So our slope is this. All right, I think my camera froze a little bit, but our slope is twisting like this as we move to the right, and it would be twisting like this as we move to the left, right? So just anywhere where y is 0 along this x-axis, we have this idea already. Again, negative here, positive here, and coming together to be flat right in the middle. What about if we increase y? Well, we're going to have 3 times something, so along the whole thing, as we move this, we've got this general pattern, but as we move this and we ask what's happening to the slope with respect to y, we're going to be increasing it. We're going to be rotating this whole thing. This is kind of hard. We've got kind of like this, and then we're rotating the whole thing, as we move in this direction. It's tougher to figure out with the squared term, but here we can at least kind of fiddle around and make sense of this. So again, we take these first derivatives, we set them equal to 0 because we're asking the question, where are we hitting that peak? Where do we stop going up, zero out, and then start going down? That point where we zero out is potentially a point where we've got a maximum or a minimum or a saddle point or an inflection point, but an interesting point. So again, mechanically, all that's going on here is just taking the derivative of this purple function, treating y as a constant, right? 9x squared, this is 0. This we get minus 18y, right? Because we're taking the derivative with respect to x, and that's 17, we get a 0. Right? So we did this in class, and I'm going to ignore all this ugly math here that's erroneous in some unknown way, but we can at least see this kind of like a grid if we look here. Right, so for each term, we're looking at the change with respect to x, treating y as a constant. 3x cubed becomes 9x squared. There's no y term here, so the derivative with respect to y of this term is 0. Right? Likewise, no x in here, derivative with respect to x is 0. With respect to y, it's 3y. For 18xy, we get 18y when we're treating y like a constant and asking, how does this change as we change x? If x goes from 0 to 1, the value of z, or at least the part affected by this term, is going to increase by, or rather decrease, by 18 times whatever the current value of y is. Right? Likewise for x. And then the 17 becomes a 0 in both cases. So the derivative, for the time being, just take it as something you're going to do mechanically. It's the step you follow. You take your function, you take your derivative with respect to each of these, and actually doing that derivative is relatively straightforward. Conceptually, we're thinking about changes in the slope with respect to either of these dimensions across a big set of possibilities, right? So again, we've got this, whatever rippling sea of z values corresponding with each x and y input, and we're asking, what's going on with the slope at any given point? Is it going up like this? Is it going up in the x direction? Where is it flattening out? Let's find those points to find our critical points. All right, so zx, zy, those are our first partial derivatives. Mechanically, again, not terribly difficult to find. Conceptually, it'll fit better into your brain the more you try to picture this. Sleep deprivation might help a little bit, although, of course, sleep deprivation is not healthy. Don't do that. All right, so what do we do next? We're doing a little bit of algebra here to simplify these functions into something that's going to turn out to be a little bit easier to work with than when I did not simplify first. And if we have time, we'll go back and we'll try and find what was my error here. But in any case, we've got these correct first derivatives. We take this derivative, 9x squared minus 18y equals 0. That's the same as 9x squared equals 18y, which is the same as y over 18 equals 18y over 18 equals 9x squared over 18. Y equals 9 over 18x squared. Y equals, not 2. Is it 2? No, that's not right. 9 divided by 18 is 1/2. This is how we make mistakes, right? But sometimes it's good to just walk through so you catch those mistakes. Y is 1/2 x squared. Good. From zy, we boil this down to 3y equals 18x. Y equals 18 divided by 3 times x equals 6x. Great. So, this... Good. All right. I was going to make a mistake here. This should be 1/2 x squared equals 6x, which means 1/2 x squared, let's put this in parentheses just so it's not 1 over 2x squared, 1/2 times x squared minus 6x plus 0 equals 0. So I'm going to break from the textbook here. Actually, let me not for a second. So what can we do with this? Well, we could ignore this 0. Right? We'll bring this back over and do the quadratic formula in a second. But what we can do with this is we can say, let's factor out that x. And now we're going to have x times x squared, sorry, not x squared, x to the 1 over 2, right? That's just 1/2 x from this term, minus 6. Cool, so we've got that. And since we've subtracted the x, we're left with a 0. Right, so that equals 0. And what can we do here? Let's just multiply both sides by 2. Well, it's 0 times 2. And what's 2 times this whole mess? Let's not use the times sign there. Just 2x times all this other stuff. This gives us still 0 equals x times, well, x over 2 times 2. This just gives us x. 6 times 2 gives us 12, so x minus 12. And this is how the textbook did this, right? So the textbook, again, multiple ways to get there. This is a better way than my instinct, right? In this case, factoring this out, we can see that this equation will be true if x equals 0, or if x equals 12, right? If we have 12 times 12 minus 12, we've got 12 times 0 equals 0. Or if we say 0 times minus 12, we're going to have 0. Those are the two values of x that make this equation true. Let me show you the inconvenient way, the way that I would do this, which is not as efficient as this. So I'm going to even start from here. So I've got 1/2 x squared minus 6x plus 0 equals 0. And I'm going to do the quadratic equation, so I'm going to say x is going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. Pretty sure that's 4ac, but conveniently c is 0. Right? So given that this is 4 times 0, we can ignore that whole thing. That's a relief. All right, b squared. Well, b is negative 6, so what have we got? We've got negative 6, so that's a positive 6. Give or take b squared, so negative 6 times negative 6 gives us a positive 36. Oh, look at that. The square root of 36 is 6, right? 36 minus 0 is 36. All over 2a, 2 times 1/2 is 1. That's pretty convenient. So what do we got? We got 6, give or take 6, all over 1. Ooh, this is nice. So what have we got? We've got either 6 minus 6 is 0, or 6 plus 6 is 12. So we still get those same answers. So we know x is going to be 0. Let's put that here. Or it's going to be 12. These are our key points to focus on. This is our, well, this isn't a critical point. This actually, let me try and make that square brackets just to give myself a hint that I'm not looking at the point 0, 12, which would be right here. I'm just thinking of this as x is in this set 0 and 12. So what is y? Well, y is 6x, or it's 1/2 x squared, but this is easier to deal with, right? So that means, let's switch colors again. Y equals either 6 times 0 or 6 times 12. So y is either 0 or y is, well, let's see, that's 60 plus 2 times 6 is 12 equals 72. So our critical points are 0, 0. I don't know why I'm writing it again, but whatever. 0, 0. So the origin is one candidate point, and then x equals 12, y equals 72 is another possibility. 12, comma, 72. Right? 12 is x, 72 is y. So these are 2 points where both of these equations are equal 0. Right? These are 2 points where in the x direction we flattened out, and in the y direction we flattened out. So this looks like maybe the top of a hill. This is maybe the top of a hill. Probably one's going to be the top of the hill, one's the bottom of a valley. But let's check that. So what have we done? We've done our first partial derivatives. We've found our interesting points, our critical points, and now we're going to check those second derivatives to see what's going on, and then we'll check the cross partial derivative to see if something funny is happening in the corners. And this relates to something I put up in the video from my other notebook. So you'll see this video on the page, on the YouTube page, which is, where did it go? What am I even looking for anymore? Ah, yes, that's right. So these cross partials. So in that other video, you'll see that we talk about what's going on in the corners. And so this example here, we've got something where we have 2 negative second derivatives. So it looks like 2 parabolas opening downward. This is hard to show from my hands, right? But they're kind of both like this. So it looks like we're at the top of the hill. But our cross partial derivatives kind of pull us up in these 2 directions. So if you imagine sort of draping a handkerchief over a grapefruit, you've got a hill-shaped thing, and then you pull up these 2 corners of that handkerchief, and you're going to have it going up, even though you've got that flat point at the very top. That said, let's jump back to this example. The example from class. So we have done the first step. We found our critical points, and what those critical points are again, these points where it looks like it's flattening out. Our second check is what's going on with the second derivative. So let's go ahead and do that over here. Zxx, well, this is going to be what? 18 times x. There's no x term here, so that's going to be y. Right? So 18x. And then over here, what do we get? The derivative of this with respect to y, zyy, that's just positive 3. Right? Now here we've got this x because of this squared term. So if x is negative, this is negative. If x is positive, then this is positive. So we're looking at x of 0 and x of 12. So this is maybe a minimum, right? Since we have a positive second derivative here in the x direction, right? So as we increase x, we ask what's going on with z. Around here, around x of 12, we've got something that's basically shaped like this, something that's opening up, right? So given that our underlying function is shaped like that, this is maybe a minimum. This 0, well, that's a little bit trickier, right? Here we actually need to dig a little bit deeper to test that. But we'll get to that when we get to it. Let's check the y. Well, this is always positive. So we're going to have something very similar here, right? So if we think about, I'm going to throw y up on this dimension, and I'll throw z over here. And we're asking what's going on around where y is 72. Well, when y is 72, we've got something opening in that increased direction for z. Right? You can imagine doing this like this. So with z, and I guess actually also flip this. Let's mirror image this. If I can do this really quick, I will. Flip horizontal. There we go. Look at this. So now I'm increasing in the y direction as I move to the right. I'm increasing in the z direction as I move up. And I've got this kind of parabola shape that I'm getting from this second term, right? I'm getting its concave up. So whatever's going on there, it looks like a minimum. All right, let me go back to not mirror imaged. Transform, flip horizontal. There we go. So, there we go. Did I freeze my camera? Let's just double check this. Okay, I don't like the looks of this. Let's go ahead and stop, and maybe this is a two-parter.